Hey guys, my name is Reese Malia. I'm going to be the maths guide and mentor for the Year 11 and 12 standard and general maths guides. So if you ever have any questions or you need someone to contact regarding your maths, please contact me. Okay, so we're going to get started with the linear relations topic, in particular the linear modeling part of the topic. In another video, I'll do the direct variation part of the topic, as well as other topics as well. So if we jump right into the linear relationships topic, your syllabus points are as follows. So I'm going to go through these and then some examples for each as well. So the first dot point there is to determine the y-intercept and gradient of a straight line given in graphical form. So if you're given that's basically saying if you're given a graph, you should be able to identify the y-intercept and gradient of that line. Next, determine the equation of a straight line, where m is the gradient and c is the y-intercept, and we want it in that form, y equals mx plus c. So I'll show you how to do that. It's pretty straightforward. Next is to determine y-intercept and gradient from the equation of a straight line. So if you've got an equation, it's being able to go to that step to determine what's m, what's c, and what they represent. Our next stop point is to construct a straight line graph with and without using graphical applications. So that's just an application of constructing straight line graphs. Next is to model linear relationships and interpret features of those relationships in a variety of contexts, noting that the y-intercept is the vertical intercept and the gradient is the rate of change. So that's actually putting these scenarios into real life context and how we can use them in the real world and what they mean. So we'll look at that too. Next, interpolate and extrapolate data from a linear model in a practical context. So interpolating is estimating data points within the range that was used to create the model. Extrapolating is estimating data points outside of the data range that was used to create the original model. And finally, identify and describe the limitations of linear models in practical contexts. So why might not they be that useful, right? We'll look into that too. So our first example here is to find the y-intercept and gradient of that curve there. So if we start off with the y-intercept, it's easy. The y-intercept is literally where the line cuts the y-axis, which we can clearly see is at the point 0, 3. So the y-intercept there is 3, right? So the y-intercept equals 3. It cuts the y-axis at 3, all right? And the point is 0, 3. The 3 is the y-coordinate, so that's what we're interested in. So your y-intercept is 3. To find your gradient, you've simply got to use rise over run between these 2 points, which is a formula you should be familiar with, where the gradient is denoted by m. So m is equal to rise over run. Rise is simply your difference between your two y values between the points, so y2 minus y1. And your run is simply the difference between the x values of your 2 points, so x2 minus x1. So if we treat 4, 7 and 0, 3 as x1, x2, and y1, y2 respectively, and we're going to get our rise is equal to 7 minus 3 divided by 4 minus 0. The difference in the y coordinates divided by the difference in the x coordinates, which is going to equal 4. 7 minus 3 is 4 over 4 minus 0, which is 4, so that simplifies to 1. There we go. We have found our y-intercept and our gradient. That is it. Now, as we move to the next question, given a line passes through those points, determine the equation of the line in that form, right? So now it's a similar question to the previous one, although we now don't have a graphical representation, we're just told what the points are. So if we go ahead and try and calculate, so basically to write in the form y equals mx plus b, all we need to find is m and b, or b or c, whatever you want to call the constant. So if we go ahead and find m first, even though we don't have it graphically drawn up for us, it works the exact same in the sense that gradient is rise divided by run, so difference in y's divided by difference in x's. So the difference in y's, well, it's 4 minus the other y value, which is negative 1. Be careful of the double negative because it does become a positive. Divided by, now we subtract the x values, right? So negative 7 minus negative 3. Again, we've got another double negative. So that's going to become on the top 4 plus 1, which is 5. And on the bottom will be negative 7 plus 3, which is negative 4. So that is going to be our slope. And so now the equation of the line is y equals 5 over negative 4 times x plus b. And then the second step is to find b, our constant, which is also will happen to be our y-intercept. So the way we find that is by simply summing in either one of these coordinates, because both those points lie on the line, so it doesn't matter which one we choose, and then rearranging to get b and make it the subject. So if we do that, we're going to get negative 1 is equal to 5 over negative 4 times negative 3 plus b, right? I'm using the first coordinate there. And then if we solve that, we're going to get negative 1 is equal to negative 15 over negative 4 plus b. So b is simply equal to negative 1 minus 15 over 4, because this will become positive 15 over 4. We take it to the other side. We then have to minus 15 over 4 from both sides. Okay, so that's what b is equal to. So therefore, y is equal to 5 over negative 4x plus our b, so plus b, which is negative 1 minus 15 over 4. And of course, yes, you could simplify your b using your calculator or just by adding your fractions to get a simplified version of your y-intercept, but that is the equation of that line. Next, we're given the following equations, determine the gradient and the y-intercept. So this is another one of the dot points on that syllabus that I went through earlier. So this is the big form we're looking at. Your coefficient of your x is your gradient and your constant is your y-intercept. There's nothing more to it than that. So for this, your gradient is simply your 3, your coefficient of your x, and your y-intercept, I'll just write as y-int for now, is equal to 2, your constant. If we look at the next example, all right, what's the coefficient of the x? Now, you might think it's negative 5, but be careful because in this case, and in the third case, y is not the subject. So the first thing we need to do is write y as the subject, and if we do that, we divide everything by 2, and we're going to get that. So therefore, now your coefficient of the x is not negative 5, it is negative 5 over 2. So that is our new slope. And our y-intercept is simply our constant hanging on the end, which now is negative 1. Not negative 2, it's negative 1 now, because we've divided everything by 2. And finally, if we do this one as well, make y the subject, I'm going to start by adding 5x to both sides and minusing 4 from both sides. Now, if I divide everything by 8, I'm going to get y is equal to 5x divided by 8 minus 4 over 8, which I can write as minus a half. So therefore, my slope in this case is my coefficient of the x, which is 5 over 8, and my y-intercept is that constant hanging on the end, which is negative a half. There we go. Nothing more to it than that. All good. Next question, plot the graph y equals 2x minus 4. Okay, so if we draw up our Cartesian plane, we know our slope is equal to 2 and our y-intercept is equal to negative 4. The way I got that is just the same as how I got all these ones from the previous question. So therefore, if we've got a y-intercept of negative 4, we immediately know that the line is going to cut at y equals negative 4. Then because these are straight lines, the beauty of it is that you only need one other coordinate now, and then you can just connect the 2 dots with a ruler, okay? So the way we can find another coordinate is simply by picking any x value we want, summing it in, getting a corresponding y value, and that will generate a coordinate that we know lies on the line y equals 2x minus 4. So we already know what y is when x is 0, but what about when x is 1? Well, when x is 1, y is equal to 2 times 1 minus 4, which is equal to 2 minus 4, which is negative 2. So in that way, we've generated a point. We know that 1, negative 2 lies on that line. So now if we plot this point, x is 1 is somewhere about here. Y equals negative 2 somewhere about there. So that is your coordinate 1, negative 2. And now if we grab our ruler and connect the 2 dots, we will now have our equation of the line right there. Y equals 2x minus 4. And does it look about right? Well, yes, it cuts at negative 4 on the y-axis, and it's got a positive slope, so it should be going up to the right. So yes, that graph looks right. We should be good. Next question. A taxi company charges a base fare of $5 plus $2 per kilometer. Write a linear equation to represent the cost C if the trip is X kilometers. All right, so this is putting the linear y equals mx plus b content into a practical perspective. So if we get on any taxi ride, we're going to have to pay a base fare of 5, plus for the amount of kilometers we travel, we're going to have to pay $2 for every one of those kilometers. So for every kilometer we travel, we times by 2. That's how many dollars we're paying, in addition to the base fare of 5. Okay, so that there is our equation of our line. And if we were to sketch that, it's going to look something like this. So it's got a y-intercept of 5, and it's got a slope of 2. But like I said, because it's linear, we only need one other coordinate, which you can find by subbing in any value of x and getting a corresponding c value. So when x is equal to 1, c is equal to what? So c will be simply equal to 5 plus 2 outside of 1, which is equal to 7. So we know that 1, 7 is a point where this line lies on. And if we again grab our ruler, we can connect those 2 points, and we'll get something that looks like so. Now you'll notice I've only graphed in the positive x and y region, which makes sense because if I was to graph anything back here, it wouldn't work, because think about it, you can't travel negative x amount of kilometers. You can only travel 0 kilometers or a positive value of kilometers. You can't travel negative 3 kilometers, all right? So yeah, you only need a graph in the positive quadrant there. This is another thing you need to look out for when graphing linear relationships in a practical context. It's not always just about the maths, it's about thinking about what the maths means and how you can interpret it, all right? So that would be your answer. Done. So that's your linear equation, and it didn't ask to graph it, but we have graphed it anyway. Next, interpolation and extrapolation. If we're given an equation, write a linear model, that is a linear model created with data points within x equals 1 and x equals 5, estimate y when x is equal to 3. Now, x is equal to 3 is a point within the data used to create the model, which is between 1 and 5. So this would be interpolation, which is probably going to be more accurate than estimating the value of y when x equals 10, because x equals 10 is outside of that range from 1 to 5. So the model might not be linear all the way up to the point x equals 10. It might start to be non-linear or show exponential behaviors at that point. But we can still assume that anyway. And the way we assume it or estimate it is simply by subbing the x coordinate in and solving for y. So if I'm going to do that now, I'm going to get y is equal to, for x equals to 3, I'm going to get y is equal to 1.5, which is the same as 3 over 2, it's 1.5, times by 3 plus 2, and that's going to give me 3 times 3 is 9, 9 divided by 2 is 4.5, 4.5 plus 2 is 6.5. And similarly, if I do it for this case, I'm going to get 3 over 2 times by 10 plus 2. So I'm going to get 30 over 2, which is 15 plus 2. So I'm going to get 17. But of course, you can use your calculator for that. So these are our estimated y values for these corresponding x values, respectively. Okay, and finally, the last question is to discuss some limitations of linear models in a practical context, which is, again, one of your dot points. So I'm just going to list a few big ones here. So one is that linear models can oversimplify complex, or should I say, complex non-linear relationships. So for example, linear relationships may assume a relationship is linear and therefore provide a linear model when it's not. An example of that is the growth rate of a tree. Right? It might be linear for the first couple of years of its life until it fully matures, but then it's not going to keep growing at that same rate years, decades, and decades down the track, okay? Because it's got to reach a max height eventually, and the tree's got to keep aging, but not keep growing as well. So that could be a relationship where a linear relationship might not be the best way to go about it. And this sort of feeds into another point where linear models are poor at extrapolation. It's another thing you can write down that's quite important. It can just ignore variable interactions and dynamics and just give inaccurate representations of data, since they assume trends are indefinitely in a straight line, when in some cases they're not, as I just said. So there are a few points. There's you're gonna expand on that, but there's not really much else to it than that. So I will leave it at that, and thank you for watching this video, and check out my other videos. Thank you. Bye.